Hello, so this is the last lecture. This lecture is kind of a reward to going through this class. This is a talk that Dr. Ruth Vanderpool and I gave to UWT faculty about 10 years ago. The slides are a little rough, but the content is really good. I think you'll enjoy it. It comes to as a consequence to some of the historical beats that we discussed in the course. We talked about the mathematics leading up to the invention of computers. This talk talks about some of the consequences of that mathematics. All right, let's get right to it. Okay, the title of the talk is the answer to life, the universe, and everything in mathematics. All right, so if you know the reference, you know it. The answer to life, the universe, and everything is the number 42, as it is discussed in Douglas Adams' Hitchhiker's Guide to the Galaxy. The punchline being that you have the answer to the life, universe, and everything, but you don't know what the question was. This answer is 2. There's another answer to life, the universe, and everything that scientists are working on, especially physicists. That's the theory of everything. You want to have one coherent physical theory that explains all the known physics and consequences of these things, and you want to be able to predict everything. Right? So this is something that they're still looking for, but what this talk is going to cover is not that. What it is going to answer, though, is any question that you can pose in mathematics, yes, no question. And I'll give you the answer and then how to use the answer to settle any mathematical question whatsoever. That's a guarantee. Okay. All right. So the answer is not 42, but it is a number. It's a number between 0 and 1. Okay, so here's what we're going to cover today. So we're going to talk about what Turing machine is and halting problem associated with the Turing machine. And then we're going to define this answer. It's called Chaitin's constant, omega. And then we're going to describe how to use omega to actually answer any question. And we're going to use a $1 million problem on how to answer that problem using this constant omega. Okay, so what is Turing machine? Turing machine is a mathematician's model for a computer. This is artist's depiction of what Turing machine might look like. And he has all the components of what you might expect on a modern computer. So this idea of Turing machine was invented before actual computers. But even though it's a little bit simplistic, it could do any problem that modern computer can solve. So in some sense, all computers are equivalent, and that's the idea of universal Turing machine. So simpler Turing machine maybe could do a particular computation, but if it's sophisticated enough, it is able to mimic every other machine or program. So you could literally compute everything. Okay, so in this picture, you see big roll of paper. So these roll of paper is divided into little segments, and each little segment can hold digit 1 or 0. Okay, and maybe you already know that computers are basically computing with lots of 1s and 0s. So that's what this is about. This is equivalent to hard disk on a modern computer, maybe a solid state drive. It doesn't have to be a disk, I guess. So the Turing machine could focus on one particular part of this storage, and we're going to call that slot the head. So the head can read 1 or 0 that's written in that space. It is able to rewrite the 1 or 0 that's written in that space, and it's also able to move one slot to the left or one slot to the right. So it's always in focus on one spot on a tape, and that's what the head is. The Turing machine has internal memory, so that's the modern computer equivalent of the RAM, random access memory. So it is allowed to be in a certain state inside. It also has movement rules that's decided per Turing machine. So depending on the internal memory state and what the head is reading, 1 or 0, it has its own rules about what to do next. So it could rewrite the head or move left or right. And it depends on, and it's also allowed to change the internal state as well. Okay, so there's a bell also attached to the Turing machine. So the purpose of the bell is it rings when the Turing machine is done computing. So when it's done, it dings and then it stops computing. I don't know if there's a modern equivalent to this, but maybe like a speaker that literally dings at you when it's done. Some kind of notification. Okay. All right. So here's a question. It's a reasonable question. So if you give a Turing machine a program, so the program is going to be already pre-written in the tape and an input. So like maybe you'll give it a function. Hey, here's a program to compute square root, and when you're done, please ring the bell, something like that. Okay, so if you give a Turing machine a program and some kind of input, the number to square root, is it gonna ring the bell or not? See, it is possible to write a program so that maybe it goes on an infinite loop, or maybe it just computes forever and it never ends. So that's a possibility that it never rings. So if you give it a program, is it going to ring or not? So let's do some examples. So what I'm saying is a little bit more clear. So let's say you have this very simple program that it takes an input, doubles the number, and see if it equals 42 or not. If it's equal to 42, it'll ring the bell, and then it stops. If it's not 42, it'll just go in a loop and try to double it and see if it's 42 or not. So if the input was 21, then immediately it doubles it and gets 42, and it rings the bell, it's done. If the input is something else though, so for example, 2, it'll double the 2, it gets a 4, it doubles the 4, it gets 8, doubles 8, gets 16, 16 doubles get 32, then 64, and now it's already past 42. There's no way to get there. And it keeps doubling, but it never reaches 42. So it keeps on going forever. So in this case, it does not halt, it loops. A better written program, maybe. So if it goes in a loop, it starts with some starting number D, and sorry, it computes the average of D and 42 divided by D, and then you do that loop over and over until you looped X times, and then it returns D. This algorithm actually computes the square root of that number. And if it loops X times and then spits out a number, it always ends after X loops. So this will always halt after doing the loop. Okay. So here's a theorem. So it turns out that there's no general method or algorithm to determine if the Turing machine will halt given a program and input. But this is surprising. So this means there's no ultimate debug machine that could read the program and tell you within a finite time if this will halt or not. So the best you could do, I guess, is to run the program. And if it halts, then you could definitively say it halts. But if it keeps on going, you can't tell if it's gonna stop in the future or if it keeps going forever. All right, so let's prove this. We can actually prove this using Cantor's diagonalization argument. So that was a beautiful argument that was given in chapter 4. We'll reuse it here. So we're going to do it by contradiction. So let's assume that such program Q exists, where Q can tell if a program and an input will halt the program or keeps on looping forever. Okay, so how do we do this? So on the left, what we're going to do is each row, we're going to list every single possible program there is. So starting with the program 0, program 1, 0, 0, 0, 1, and so on. It'll iterate all finite programs in each of the rows. And on different columns off the top, we're going to write down all possible inputs. So 1, 2, 3, 4, 5, every single possible number you can throw into the program. And notice that we could run Q, the program Q, to determine which of this combination will halt and which of this combination will loops forever. So you can determine one or the other in every possible combination of program versus inputs. So for example, if you're running this program 1, 0 against the input 4, maybe you know that it halts. So we'll mark that with a bell. And if it keeps on looping forever, we'll just mark it with L. And so by running the computer Q, now you have constructed this grid matrix of all possibilities. Now we're going to create a new program called P. And what we're going to do is we're going to create P so that it disagrees with every single program on this list. So this program, the first program with the first input, this halts, right, from the grid to the left. So what we're going to do is we're going to design this program so that it loops forever with the input 1. And on the second slot, we know that this this halts in this combination, this program and this input. So we're gonna loop forever. And then the next slot, this thing loops. So we're gonna halt instead, and we're gonna go through the diagonal. And you just flip the bell to a loop and loop to a halt. And so on. Okay, so this is how we're going to program it. So if you can tell that this is going to halt, you're going to loop forever. If it looks like it's going to loop forever, then we're going to halt instead. So you just use this program Q as a subroutine to determine what you're going to do with this program P. But now you have a list of outputs with different inputs, 1, 2, 3, 4, and so on, that disagrees with the first program because it disagrees with the first program because it loops in input 1. It disagrees with the second program because it loops with the input 2, and so on. It disagrees with every program on the list. But that's a contradiction because we've listed all possible programs. So that means that we've created a program that does not exist. So that's a contradiction. The only way to avoid this contradiction is to, the only thing that we really assumed was this existence of this program Q that can tell if a program and an input will loop forever or halt. So no such program actually exists. Okay, so we have enough background to actually answer the question we posed at the beginning of this talk. This is what's called Chaitin's constant, omega. So what is omega? Omega is a probability that the Turing machine will halt when it's given a random program. So I have to describe that a little bit further. What do I mean by random program? What we're gonna do is we're gonna flip lots of coins. So we'll get heads or tails, and we're gonna translate those heads and tails into ones and zeros. So we flip coins, turns it into ones and zeros, and then if you just do that, you just keep going forever. So let's end the program by including some kind of ending sequence. So let's say when it first encounters the sequence 10, 10, 10, that's I just arbitrarily chose that this is binary for 42. When it encounters that sequence, the program ends. So this is a finite program. Okay. And then the rest of the tape is going to be filled with zeros. Okay. So let's recap. Every program ends with this ending sequence. And if this program is n bits long, then probability of actually getting this program by flipping coin is 1/2 to the nth power, because when every time you flip a coin, you have 1/2 chance of getting it correct by 1/2, right? And it has to get n bits correct in a row. So that's the probability of this program running. Okay, so it is a probability, and I guess I described what the omega should be, but how does this answer, how is this the answer to the life, the universe, and everything? Let me describe that to you. Okay, so let's use an example of Riemann hypothesis. So this is a question that mathematicians really want to know the answer to. And the statement itself isn't too important, but what's important is that it's a very precise statement that whether there could be a yes or no answer to this question. And if you can settle this, if you can show that any root of this zeta function lines up in this particular line, then it's worth $1 million. If you can prove that, or if you can prove that, if you can find an example of a zero that's not on that line, it's also worth $1 million. So we want to settle this statement. And we're going to use omega to do it. Okay, so what we're going to do is we're going to write two different programs. One we're going to call optimistic program. So that's going to be this gold colored Turing machine. And how this program runs is relatively simple. So you teach it all the mathematical logical things you could do, and it'll systematically apply mathematical logic to statements that it's aware of, and it tries to prove the Riemann hypothesis. So it just randomly, not randomly, systematically tries to apply every argument. And if it recognizes that it has accidentally proved the Riemann hypothesis, then it rings the bell and halts. But otherwise, it keeps on looping and try to apply different arguments until it finds a proof. Another program, pessimistic program, this Turing machine will be colored purple, and it will apply rules of logic until it disproves Riemann hypothesis. The opposite of Riemann hypothesis is proved. Okay, so you write these two programs, and let's say n is the length of the longer of the two programs, whichever one that's more complicated. So we're gonna need that number n. And what we're gonna do is we're gonna mass produce Turing machines. So in fact, we're gonna create every single possible Turing machine with programs running length n plus 1. So it's something that's just a little bit longer than the programs, the pessimistic and the optimistic Turing machine. And we're gonna all create it, create them, these Turing machine. And these Turing machines are created so that its size is proportional to the length of the program, or sorry, it's proportional to the probability of the program. So shorter programs, remember, is more likely to be chosen. So those are larger Turing machines. And the longer programs are much smaller because the probability is 1/2 to the nth power. So these are Turing machines of different sizes. We have a lot of Turing machines. We're gonna prepare 2 buckets, and we're gonna mark line on this bucket. So let's say this is exactly 1 liter size bucket, and wherever there's the omega, so omega, remember, is the probability that the Turing machine halts. We're gonna put a line on the bucket that marks that probability, that many liters. And then, so this is the bucket for Turing machine that halts. And we're gonna create another bucket for Turing machine that runs forever. And we're gonna, that probability is going to be 1 minus omega. So we're gonna mark that on the bucket there. Okay, now next step is to run all the Turing machines. So all the Turing machine with their respective programs are going to run, and they're gonna try to see if they're going to ring the bell and halt, or it keeps on running forever. So our next task is to sort these guys. So as it runs, some of the Turing machines will finish computing, rings the bell, and stops. So there's a lot of these out there. So we're gonna start to pick them up. If they ring the bell and stop, you're gonna toss it into the bucket of the Turing machines that halted. So it's gonna start to fill out the bucket. Okay. It's never gonna pass omega, because omega exactly is all possible Turing machines that programs that halts, and we didn't make infinitely many Turing machines, right? We just went just enough so you have all the Turing machines to the same length of the program plus 1 of the 2 programs that we're interested in. Okay, so I know that as we toss in Turing machine into this bucket, I kind of draw it zigzag, but maybe it needs to be a little bit more precise. So you might have to pack it down. You might have to stick your feet in the bucket and squish it, or maybe liquefy this so that we have exact measure of the volume of the Turing machine that halts. After it gets very, very close to omega, you will start to see that some of the Turing machines that are still out there is a little too big to fit in this bucket. So if they halted, then you'd put it in this bucket and it'll go over omega. We know that's not going to happen. So this must be a Turing machine that never halts. So as soon as this gets closer and closer, you know that you can toss some of the larger Turing machines into the bucket of Turing machine that runs forever. Okay, you keep doing this until both the optimistic and pessimistic Turing machines will be sorted out in one bucket or the other. It turns out that if you run it long enough, the only Turing machines that will be left eventually will be the smallest Turing machines of length n+1. Okay, so if the two Turing machines that we're interested in, the gold and the purple one, optimistic and the pessimistic one, there's four things that could happen. If optimistic Turing machine rings, then we have a proof for Riemann hypothesis. If the pessimistic Turing machine rings, then we know the Riemann hypothesis is false. It's in fact disprovable. There's two other possibilities though that you might have not considered. It's possible that neither Turing machine rings. So they cannot prove one way or the other. So that is a possibility. This is a mathematical question that's undecidable. So it neither has proof nor disproof of this fact. And the fourth possibility is that they both ring and stop. So this is a case where a statement and the opposite of the statement is both proved. So mathematics is inconsistent if that happens. So Gödel's incompleteness theorem says that for any consistent theory that's complicated enough to handle arithmetic, there are some statements that could be neither proved or disproved in the theory. So it is possible that Riemann hypothesis or some of the other questions that you want to answer comes in this category of statements that could not be proved or are disproved. So some statements are out of reach. We learned that from Gödel's incompleteness theorem. So what are some of the examples of things of that nature? So there's what's called axiom of choice in mathematics. It has been proven that this axiom of choice cannot be proven and it cannot be disproven. And in fact, you could choose it to be either, and you could have a consistent mathematical theory, including this or not including this. So that's one example. That's why it's an axiom. So you can choose it to include it in your mathematical theory or not. Another important example of something that's a little bit out of reach is computing the Chaitin's constant itself. So it turns out that this omega, it's a probability, and you can show that it exists, but it's uncomputable. What I mean by that is that you can put bounds on it, but there's no program you can run for a finite time that guarantees that this number is true up to this many digits. So you cannot create a program like that. It's actually a number we are not able to compute. And it should be that way, because if we could actually compute it, then actually you could actually use this to solve the halting problem as well. And we know we can. And these are some sources if you find this talk interesting. And I know this is a video, so you can't really ask questions here, but please post on the class discussion board or send me email if you have any questions about this talk. Anyways, I hope you enjoyed the talk. I think it's a really cool topic. So, okay, so this concludes the course. Good luck on the final exam, and I will see you around when we can.